My name is Jailbek. I'm a postdoctoral researcher at Princeton University, and here with me is Joseph Ellisor, a PhD candidate at Princeton University. Today we are going to talk about our work on a vertical stack voltage regulator for ultra-high current microprocessors. Throughout the development of computing, chip manufacturers have been able to keep shrinking the size of the transistor while increasing their speeds and decreasing their operating voltage. And the power density of the microprocessor is growing rapidly to over from zero point 0.2 watt per millimeter square to over 4.5 watt per millimeter square. And now at the same time, the overall die area continues to get larger and larger. So we are talking about over 1 kilowatt per processor. And we are putting many of these processors in a given server, which creates a lot of challenges in designing the power electronics for these applications. One good solution to improve data center power delivery efficiency is distributing power at 48 volt instead of 12 volt, which reduces the current for the same amount of power. However, the challenge becomes how do we design power converters that can take 48 volt and step it down to deliver the low voltages and ultra high currents needed by microprocessors? How do we design them with high power densities like microprocessors? Our solution utilizes a merged two-stage architectures, which consist of a 2-to-1 switched capacitor on regulated stage and a 4-phase buck regulated stage, whose operations are coupled together. We can remove the large DC decoupling capacitor between the two stages, enabling a higher power density and allowing the buck inductors to supercharge switched capacitor stage. The first stage operates at a lower switching frequency to improve the system efficiency, while the second stage operates at a higher switching frequency to improve the system speeds. What's shown here is one building block of our topology. And this topology can be extended to further building blocks like Lego blocks. So we call this architecture the linearly extendable group operated point of load architecture. And one very important function to develop a very high output current converter is that we need to get automatic voltage and current balancing. If the voltages and currents are not balanced, and you need to use sophisticated active control, then this building block approaches doesn't make sense, or it becomes very expensive. A major advantage of this architecture is that it automatically balances the input voltages and share the output current evenly through each building block without any active control. We derived large signal average model for our topology and compare it with the simulation results as shown in here to verify our mechanisms. Recently, there has been a lot of discussion on vertical power delivery. Intel has published their power via technology with signals coming from the top and power getting in from the bottom. And Tesla has published Tesla Dojo. The benefit of vertical power delivery is that we can greatly reduce the interconnect length and enable better signal integrity, resulting in many system leverage advantages.
Thanks, Jail. So to enable vertical power delivery, we actually customized and fabricated a coupled inductor that's shown here. And so power comes in from the bottom of the core and then exits from the top. And it has a pretty small footprint, it's 12 millimeters by 13 millimeters, and it has a height of 5.25 millimeters. And so by leveraging this multi-phase coupling, we're able to actually reduce the energy storage requirements of the inductors themselves. This allows us to achieve a lower phase current ripple throughout each of the phases of the multi-phase buck, and that pretty much translates to a higher efficiency of our second stage. As well, it's important to have a very fast speed when the load current is constantly changing in these CPUs, so multi-phase coupling allows us to achieve a faster speed. And here's some further reading here if you're interested in actually understanding what multi-phase coupling actually does and how to quantify these benefits. So we implemented a 3-submodule converter here, and each submodule steps down 1/3 of the input voltage. So in this case, it's 16 volts down to 8 volts. And then the second stage will step down the 8 volts down to 1 volt, or the point of load. And so here, each submodule handles 1/3 of the overall output current. So in this case, 260 amps, because we designed our system to handle a full load of 780 amps of overall output current. And so here you can see the assembly procedure for the vertical stacked converter here. So the first step is to assemble the switch capacitor stage, the first stage. And you can see here there's those like copper rods there on the switch capacitor stage. And so those are actually like the interconnects that connect between the first stage and the second stage. So once we assemble the buck stage, we place it vertically right on top of the switch capacitor stage. And then lastly, we assemble the coupled inductors on there. And so this full system, power system assembly here is 46.5 by 16.5 millimeters. So that's an area of roughly 770 millimeters squared. The height is 16.65 millimeters. That's roughly a volume of 0.78 cubic inches. And we actually brought the prototype here with us. So if you're interested in seeing it up close, you can come up to our poster session later, and we'd be more than happy to show you, and you guys can touch it and see how it works. And so here, what we did is we basically took that power stage and we affixed it to all of the gate driving and control circuitry. And to replicate some of the liquid cooling setups that are now being used in data centers for high TDP processors, in our lab, we submerged it in mineral oil, and we circulated the mineral oil here to sort of help stabilize the temperature. So here's a video of it actually running in our lab. You can see our experimental setup here. And so this video is actually taken for it running from 48 volts, stepping down to 1 volt at the 780 amp full output current. And the liquid cooling here helps us to keep the semiconductor devices, keeps their junction temperature stable at 95 degrees Celsius, which is below the operating temperature for them. And you can see here the switch capacitor stage just steps down the input voltage into the 3 different voltage domains, and the buck will step down 8 volts down to 1 volt. So with this prototype, we're able to achieve a 91.1% peak efficiency and a 79.2% full load efficiency. This is without the gate driving losses included, and this is for the 8 volt to 1, or the 48 volt to 1 volt condition here. And so on the right, you can see that we benchmarked our converter against other 48 volt to 1 volt solutions, both from academia and industry. And so if we were just considering air cooling for our system, and sort of considering the cutoff of like where we call it like the peak load at 95 degrees Celsius, the same condition that we had for the liquid cooling. The current area density is roughly 0.59 amps per millimeter squared, because we're able to push for like 450 amps out of it. But if we consider the liquid cooling, we can get over 1 amp per millimeter squared. And we're switching our second stage here at 1 megahertz, which is amongst the fastest that we've seen here for these 48 volt to 1 volt converters. And to our knowledge, this is actually the highest power densities that have been reported for these 48 volt to 1 volt converters. So to wrap everything up, we leverage the merge 2 stage architecture that JL explained. We use vertical power delivery and a vertical coupled inductor that we customize, as well as liquid cooling to achieve a 1 amp per millimeter squared current density, 1000 watt per cubic inch power density, and a 91.1% peak efficiency. But this is just the beginning. As you can see, 1 amp per millimeter squared, that's still not close to the power densities of the processors themselves, as we're talking about 4 or 5 amps per millimeter squared. So on the right here, you can see the weight and volume breakdown. And so even though we have a very switch-heavy topology, you know, we leverage a lot of semiconductor devices because these are what are dense, what are small. You can still see that the switches are really not occupying too much of the weight and the volume. It's still dominated by the magnetics, it's still dominated by the capacitors, and it's still dominated by the copper. So future direction, roadmap to achieve these higher densities is to leverage higher switching frequency devices so that we can further shrink down the size of the passive components, as well as leverage some advanced packaging techniques to try to reduce the amount of PCB and copper that we have, so that we can really achieve those high densities that we need for these modern microprocessors. Yeah, thank you everybody for attending our talk, and we'll be at the poster session if you guys want to come and check out our prototype and have any questions.
Yeah, thank you. And yeah, question please.
So just a quick question, try to understand about what your transient response looks like, and also what you are doing on the cost comparisons for the other solutions or traditional solutions.
So your first question was about transient response. So in theory, the coupled inductor here has a transient inductance that allows us to achieve a response of close to 5 amps per nanosecond. We still haven't really verified the transient response experimentally yet. That's sort of the next step, is look into the control and verify the transient response. I didn't quite catch your second question.
Second question is how about the cost considerations? Do you guys compare some of the cost factors with the other traditional solutions, or?
Like the price, right?
Yeah.
Oh, yeah. Well, not too much for this one. So the customized coupled inductors here are actually quite expensive.
Yeah.
Everything else is not, but we didn't really do a detailed cost comparison or anything like that for this.
Okay, cool. Just curious. Thank you. Thanks.
Problem.
Thank you.